Okay. First things first, I have just posted a couple of hours ago what I call your current extrapolated grade, just to see where your standing is. And as well as your what I call homework grade and quiz grade. Basically, with homework grade, we go to homeworks, we drop the lowest score in the average, okay, to 100, and then the same thing is done with quizzes. Meaning quiz, there's that one quiz that we did online, and the rest were in-class assignments. That's what counts as a quiz in this class. So that the same rule applies. We drop the lowest score. So currently you have 6 or so graded homework. So basically 5 best of those are what plays into that score. Make sure that my accounting and your accounting is the same. Okay, so that's first, so that you know how this thing, how the grade is computed. And then I took exam 1, and right now we're missing exam 2 and exam 3. Exam 3 being final. So exam 1, I believe, is worth 20%. Exam 2 is 25%, and then final is 25% as well. Yes. That's on syllabus. Yes, that's piled together. It's scaled to 100 and piled together with in. Oh, it is. Yes. So that's all quizzes. So essentially, then I write now in your what I call extrapolated grade. Okay? That's what's taken. Exam 1 is that's your performance of all exams, which it is not, but that's the best we have right now. If your overall score is 60 or below, that's a problem, and we need to work on that problem. So step 1 that I'd like for those of you who are in that category is I have posted a practice exam 1 from last spring. So go to those problems, and I will post solution 2 days from now, just for additional practicing specifically loops is something that will, or mechanics of programming is something that we carry forward in all the problems. For those of you who don't want to practice exam 1 or identify any problems, you can safely ignore it, but I will post that solution. So go to TA, go to, everybody knows how to find a tutor for this class? Yes? Tutors, multiple ones. Schedule a time, schedule or come to office hours, either in you or mine, and work on those problems. Make sure that you know how to do that. The second part is that if you just focus on exam 2, is there's plenty of practice problems posted. There's from practice problems from chapters 4, 5, and 6, and then there's 2 practice exams, and the problems that are not going to show up because we didn't cover them yet are removed that part. Okay? Any questions about that? So exam is on Wednesday, November 20th, and everything. So formally, we are not covering what was covered in exam 1, but it's not that you cannot know what a for loop is and do well on exam 2. So it's all implicitly built in there. Okay? Because the exam 1 was sort of just like a mechanics of programming that is helping us now actually solve something. And we will also have those errors, like Lecture 4 on the errors. Okay. Any questions? Everybody ready to study? What I will also do to help against fail, so a lot of people approached me if you can improve somehow the grade that you have from exam 1 without retesting everybody. That's hard to do, to be fair. So what I'm going to do is I will basically take the better score between exam 1 and exam 2 as your exam 1 grade. Okay? So we can do that. But that still means sitting down and working hard on whatever, being honest with yourself, what it is that you don't know, and then asking for help. There's plenty of help available, but nobody can silo it in your brain. You have to sit down and work through those issues. Okay?
So if you did better on exam 1, will there a
That's going to stay the same, okay? But if you do better on exam 2 than exam 1, then I'm going to replace exam 1 with that grade. Okay? So it is getting, it's still a tall order, okay? So take it seriously because exam 2 is just piling on everything that was there in exam 1. So in itself, and this is not the case just in 310, that's the case for every class you have. It's just the semester is getting tighter and tighter, right? So take it, you know, it's an opportunity, but at the same time, start studying today. Okay?
I'll talk. Sorry, teaching transport next semester.
Yes, I'm teaching transport. Yay. My favorite topic. But watch out, I don't graduate before that. So I'm going to have to tone down whatever it is that I normally teach in transport. But we're going to have fun, and we're going to find a way to incorporate Python in there, trust me. And I think Mingy will be the TA, so we will incorporate Python in there. Are you ready for transport thinking? Huh? That too. Well, we can talk about that. All right. Okay? Questions? Ready to study and ace that exam too? All right, so let's get back to our programming. We are concerned about programming Gaussian elimination. Does everybody have some rudimentary code from last time? Do I need to post mine?
Yes.
Probably? Okay. I will post mine, but let me first review and then we will get to that. So, our concern is programming Gaussian elimination because I don't want to do things by hand. By hand, I can do all kinds of things. We know by now that I'm not going to change the solution of my system if I multiply a row by a scalar, if I take a linear combination of two rows, each row is equivalent to an equation. I'm not doing anything to the solution of that equation if I multiply everything by 2, right? Both sides, that is. I just do have to be careful to work both with A and B's, okay? Which is why we often kind of work, when on paper, we're working with this augmented matrix that has B's in there, so we basically make sure we're making changes to those B's as well. All right, now I have to teach a computer how to do things, and we know by now that computer is actually pretty stupid unless it's programmed to be smart. And since you're programming it, it's going to be as smart as you program it. Okay? So basically, if I have a matrix like this, I can't say to computer, oh, please eyeball the coefficient I should multiply this row with. There's no eyeballing, right? You have to tell computer which precisely coefficient it's going to do every time. Okay? So if I want to eliminate this, what I'm referring to as A21 when we're basically using mathematical notation, not Python, then basically I have to find a scalar, and we were referring to this scalar as C, to multiply my first entire row, and then add it to this row, and I want the result in this location, this is what I'm going to be replacing. I want it to be 0 right here. So basically I can say C times A11 plus A21 is equal to 0 and find what that C should be. Okay? And the same thing for every row below that. So basically what we actually end up doing is here this is going to get transformed into a matrix where I have a new row. I'm going to multiply this row 1 by A21 divided by A11 and subtract from row 2. And that's going to do it. And the same thing, it's always basically whatever it is that I'm calling these coefficients, this divided by this, okay? And then subtracted from this row, times the first row and subtracted from this row, or this divided by this, whatever this is, however I'm referring to it. Okay? So once I do that for what we call this pivot position, Then I move to my next pivot position. This is now changed. I have changed this. Okay? So that's why I'm referring to it as this tilde. Okay? And after I change it, okay, then I'm going to again behave the same. My coefficient will be this divided by this. Okay? Multiplying this row, and then I basically subtract that from this third row. And that's how I keep going. If my matrix is larger, then I just do that. So let's take a look at the code that we basically wrote last time, and let me see how it's named, and then I'm gonna I actually worked with this template, so I'm just gonna I'm not gonna rename. I'm just gonna upload that template to my file. I hope it's saved. Files, code, upload. Oh, is it in downloads? That's probably it. Please double check that it's actually full of values. So I have created a function forward elimination that works with my matrix A and right-hand side B. I examine the shape. This is my standard thing. If you need it, put it on your cheat sheet. This one line will be acceptable. And I'm just here printing something. If you don't give a square matrix, there should be something said about that, though we're not basically doing anything else other than giving a warning. And here's what it actually does. So basically for every j that is, right now I'm working with pivot element A of jj. So initially that is a 0, 0, right? For all of the rows, basically I loops through all rows below j, right? That's why I'm starting from j plus 1. So this is this eliminating below this j plus 1, and I'm going all the way to the last one. This is my coefficient. It's that current A in that row that I'm working with divided by my pivot element. That's my coefficient. And I'm replacing my row I, which is the row that I'm working with the same row minus that coefficient times my pivot row. And recall that this basically is something that takes the entire row. This is row I of matrix A. Yes? When I put the column, that means everybody, so all of the columns that I have for row I. So it's going to work with the entire row. And then I do need to do the same operation with B, right? Because I got to work with them at the same time. And that's it. It's kind of short piece of code, but because I have a nested loop, it's going to first work with A0, 0 here, right? For j is equal to 0, that's going to be the first one. My first pivot element is A of 0, 0. I'm going to go through all of the rows below that element and eliminate. Then I'm going to move to j is equal to 1. And then I'm going to work with all of those below. And that's precisely what we were doing here. First, we eliminated everybody below this element, initial pivot element. Then we move over and eliminate everybody below. It's just that in a 3 by 3 matrix, I don't have a lot of them below. And technically, then we move over, but there's no one below. So this is why my J goes through n minus 1. But code would work correctly even if I put n, because there's nobody below the last row, so this I loop will not execute. And then I return my result. That's my elimination. So here we typed in A and B. And if I basically execute, I'm going to see that indeed I have zeros where I need to have zeros. And if you compare it with your written notes, this is the same example that we worked out in class. It's actually, it so happens that the choices of coefficients are the same. Now, one thing though, so this is now an upper triangular system, right? I have zeros here below. And my B is shown as a row because we don't have all 1D arrays. This doesn't always have to be precisely the same that you would find by hand, because maybe by hand you were using slightly different coefficients. But they will still, hopefully, have the same solution, even if the systems look slightly different. So these choices of coefficients and what rows you're working with, they do matter in how this system actually looks like. But solutions should be the same. Okay? Excellent. So now I need back substitution. And we know in back substitution, okay, so I'm just retyping things and doing forward elimination again. I have, basically now I want to form the solution, and first this is just allocating memory for it. I know that it has to be the same size as my B, so I'm gonna do that. And then if I was doing my solution by hand, I would start from the last element. Let me show you what we did by hand. If I go to my documents, it's here somewhere. There we go. This is what we did when we were solving things. So basically here my x2 is b2 divided by a22 in Python notation. Then basically my x1 is b1 minus a12 x2. This is what I already have computed. Divided by a11. Yes? And x0 is b0 minus a01 x1, a02 x2, so divided by a00. Everybody sees that? Cool, this is all great by hand, and you will have no trouble other than just working out the math correctly. But the problem is, like, I want to program this. I don't want to type in. If I have 20 of them, I don't want to type in 20 equations. That's not efficient coding. So I need to find the rule that does this. One thing that I can safely type in is this last one is always, I just have that the last element of this is this last element of B divided by this last pivot element or last diagonal element of A. Everybody sees that? Excellent. Now I have to figure out, all right, what am I going to do with the rest? So I can definitely here say that if you want to actually initialize things just to at least have something, I could say, well, xn minus 1 is equal to b n minus 1 divided by a of n minus 1 n minus 1. N being the number of them that I have. Everybody okay with that? Now what I typed in last time is like, okay, I need to figure out efficient. Whatever it is that I'm doing, there is some there's a sum going on here, right? This A11x2, and then in the next step, it's A01x1, A02x2. I'm working with x's that I already have, and as I keep going, I have more and more of them. So there's some sum that is changing. And if I can't now, this very moment, figure out what that sum is, what's very useful is just naming it somehow, S. Okay? So I'm going to call it S. If it's a sum, I already know that, well, S, I can initialize it with 0. Okay? And then I'm going to have some code calculating S. And whatever that is, that's going to be some for loop. I see that it's changing and growing. But I'm just going to leave space for it now. It's B of that, whatever is the current x that I'm working with. It's B minus that sum S divided by the same, so I can see 1, 1, 1, 1, 0, 0, 0, 0, 2, 2, 2, 2. That's a pattern. If I'm calculating, what am I calling it? X of I, it's a B of I minus this mysterious sum divided by A of I. Does everybody see that?
You want to put the S equals 0 outside of the loop? So
Yes, so there will be some loop here that I don't have right now. Dot, dot, dot. Okay. And then after I'm done with that loop, my X of I is B of I minus this sum that I didn't calculate yet, divided by A of I. Yes? Is everybody comfortable with what I wrote right now? Any questions? So when you see a pattern, write down step by step what you know, and that's going to kind of propel you towards what you don't know right now. Okay, so this S, okay, takes, so no matter what, I have A1 for X1, and then here, so I'm working with A's from the same row that my X is from, yes? Because I have 1 here and zeros here and nothing here because, well, there was nothing computed. So technically, I'm going to loop over all of the A's that I have in this row and those X's that have been computed already. Yes? So here at this step, the only of calculating X1, the only X that is already computed is X2. Right? The one below X1. Yes? So I'm going to take A12 times X2. That's what I have here. Then when I move to calculating X0, okay, I'm going to take A01 X1 times A02 X2 in this sum. Yes? And then I'm going to subtract it. Everybody sees that? So again, we can say, so it seems that I am using all X's that have been computed already. And if right now I'm trying to calculate X of I, and I started with X of n minus 1, right? All of the ones that have been calculated, apologies. Oh no. Okay. All right, bye. My phone goes to my computer and my phone. Okay. Gone. Apologize. All right. So basically, I will literally type in that. Okay. So it seems I'm using all of the X's that have been computed already. I started with n minus 1, right? and I'm working with I. So it's basically n minus 1, n minus 2, n minus 3, if I have a lot of i's, right? Down to I plus 1, correct? Yes? One more than I'm currently working with, and that's x of I. You kind of ask yourself, who am I right now in this step? I'm calculating x of I in my ith row. I calculated all of the x's below down to the last one, which is, you can flip it, it's I plus 1, I plus 2, all the way to n minus 1. Yes? But I think literally writing down, it seems that I'm using all of the x's that have been computed already, and then try to translate that to the notation you're using in the code. Or you often also have to decide on notation. I decided that I'm calling them I. I could have called them Z, doesn't matter. Okay? Questions? So my sum is basically going to start from 0, as all sums do, and then I'm going to do a for loop. I'm going to use that J for that in range. I'm going to write down this range. And I have to remember that rule that range will not include the last one. So if I type in I plus 1, it's not going to be included, so I got to go 1 down. And my step is minus 1. So in range, I can step in regular increments, in which case I don't need to write down what my step is. But if I want to change the step from plus 1, then I have starting point, ending point with 1 additional down the line, minus 1. Yes? Range function. Speaking of the topics from exam 1. Okay, so what am I adding to this sum? I'm working with x of j, which is those x's I'm talking about, times a of what? I also have it right here written.
Do you start with the b value?
Hmm?
Do you start with the b value, or is it...
That's right here. So from which row am I taking my a's? Yes, the same as x. And this value has to match my x. That's it. And this sum will have different number of elements depending where I'm at, right? Because the number of already computed values will change. Now let's see if I had any typos here. I'm going to print my solution at the end for this particular case. And note that here I kind of typed in this and then I repeated for it. It doesn't matter. Technically, I can comment this part. I was just trying to type in something that I know, or starting point. So I can either type in and then start from n minus 2, or just not type in anything. This will work. Either way works. Questions? Yes?
What is the first minus 1? Like, why is range and minus 1 minus 1?
I'm going down. Because otherwise 0 will not be included. I don't like the way range function works, but that's how it works, unfortunately. that ending point will not be included, so I have to go one down. Okay. Now, I could have typed in this as a growing, like going from I+1 to, that could work too. Let's see whether this works. So my solution is 2, 2 minus 1. And I can check whether the result is correct simply either comparing to what np.linalg.solve would do, or multiplying a and x and deducting b. And the result should be 0, 0, 0. Up to some round of error, maybe. Yes? So it seems that I've done this correctly. Has everybody managed to type this in? Do you see the mechanics of it? Now to translate to the sums that we've, whoa, wrong presentation. The sums that we've worked with before, what I have basically typed in the language of those sums and summation forms, is I have calculated this in that back substitution. So it's x of I is b of I minus sum of all of the computed xj's already and multiplied by coefficients from the same row of a as my I. So this is that sum s divided by a. Yeah? In your practice exam, so you can test whether you understood this. In your one of the practice tests that I posted, you have a job to program forward substitution. So for a lower triangular system. Yes? All right. So we have just written this code. And this hopefully now works. Okay? Let's type in a different, so we can also create a function. Okay? So now I'm basically just, I was just typing in the code. So I can just take this code that works and type it into this function. I'm just actually gonna do so define my x as zeros, just to save the space. N is the length of b. And this needs to be indented. And I need to return x. And that is basically a function back substitution A or B that returns my result x. So this is just putting my code into a function that I can use. So again, this function back substitution, it takes input A and B and returns x. And then I can define a function, Gaussian elimination, that takes A and B. It first does that forward elimination that I created last time. And I save it into the same, I kind of overwrite my, I overwrite my values of A and B by this forward elimination. And then x is back substitution of A and B, and I return x. So this is now a function that you should have it in that template that I posted just now. And if not, you can just type it in and create functions. Okay, now that I have functions, let's try to use them on something else. So here there is some 4x4 system. So I have A that is 4x4 and B that is 4x1 or 1x4 rather. And I'm basically using my Gaussian elimination function. And I will check the result, so I can print my x. And I can also check whether multiplication of a times x minus b gives me something very close to 0. So again, up to a round of error. Let's see. Moment of truth. Whoa. Okay, what did I do? Check the result. Oh, I did not execute this. All right. Let's try this again. I still did something. This needs to be, so all of the cells have to be executed. All right. It works for this 4x4. So what we will do to analyze, and that's going to be your quiz for today. I'm just going to explain what you're going to do, but we're going to open up a quiz, and the results should be done actually by Wednesday, and there's a reason why. So I'm going to now ask you to analyze how fast is this? All this 3x3, 4x4, that's all nice. We know that proper engineering problems don't come in 4x4 form often. They come in million by million, okay? And even million is not enough to really properly discretize your reservoir. So it's very actually important that these functions are optimized and as fast as possible. Now it appears that this should be fast. I mean, this is blazing. It just returns the result right there. But what we're really doing here, let's just analyze back substitution briefly. So here I have, this could go n times, right? And what I'm doing here is I'm calculating this sum. Let's say that for the sake of the argument that it goes n times. It goes less than n times every time I have. Right? What I have here is I have an addition and multiplication and addition. So two additions and multiplication. Those are so-called 3 floating point operations. Now, they are fast on your computer, but they're not fast as 0. They do still take a finite amount of time. And that's actually, when you have the speed, so on my computer, processor speed about this Mac. So this Mac is not very fast, but it's going to say 1.6 gigahertz processor. Gigahertz is 1/2, and giga is 10 to the 9. So it essentially does about 1.6 times 10 to the 9 of these operations per second, give or take, if nothing else is working. Okay? So if I'm solving a system that needs a lot of these operations, say that I have a million system, million by million, okay? That's 10 to the 12, right? Operations. So let's say that I have to repeat something 10 to the 12 times, then I'm going to feel it, even if I'm just adding things. Okay? And the larger these systems that we want to solve, it's going to feel them more. So I'm going to ask you to actually time your functions. Okay? And I'm going to show you on the slide how the code looks like for timing. So basically you can import timer, and you're just going to start your timer at some point. It's going to record that as a starting point, and it's going to measure things in seconds. And then you're going to do whatever code you want to measure, so Gaussian elimination of AB, right? And then you're going to end the timer. And I'm going to ask you to do that for systems of fixed number of size. So we're going to create a random matrix. Now we can use that np_random.rand. Create a random matrix that is, for instance, 100 by 100, and B that is 100 by 1. solve the system, time it, record it. And then I'm going to move on to something that is 1,000. 2,000, 5,000. By 10,000, you might need to wait a long time. Okay? What we coded is actually kind of the slowest way to do things possible, just to learn the mechanics of it. This is how it looked like at some point. Timing on, this is actually my older computer that was a little better, but here's this computer, okay? So for 10,000 by 10,000, so my A is 10,000 by 10,000. I created a random matrix, and then I created myself a B. That was done outside of the timing, and then I just timed how much it takes to solve that. It took how many seconds? 1,600 seconds. That's already, okay? And again, this is not a large system by contemporary engineering standards. Okay? And especially if I have to constantly solve, not just solve it once, but constantly solve the systems for different scenarios, it piles up. Okay? Now, we can also see that there is np.linout.solve, which is not necessarily Gaussian elimination, but just for you to show you how optimized code looks like, and close to 0 seconds. It's probably just a few seconds. So how fast something runs doesn't matter. So we are learning here how things are done, but then there's people whose job is actually to make things faster, because, especially when we're going to execute something multiple times over and over. Okay? So again, your quiz will be we're going to open up a quiz, and you're going to report those values into a form so we can actually see what the entire class have done. And results will vary. Okay? Your computer is different from mine, you're going to get different results. You might have actually something open that is crunching some other numbers. That's going to slow down your computer. Okay? So there are still certain things that you have to take into account. Yes?
So we just have to sit there for 30 minutes?
Yeah, you have to have your computer open. So do that overnight. And do it in a for loop. So it just executes and hopefully returns and reports the results. Prints them out. So you will see, you might get angry at your computer, okay? Which is why this is going to be recorded by Wednesday, not by tonight. Yes? So let's do 1,000, 2,000, 5,000, and 10,000. I will post, but 1,000, 2,000, 5,000, 10,000. See what you get. For a number of people, I saw on 10,000, I did not get reports. Okay. Because people were not willing to wait. Yes. Yes. 4 times, create random matrix A and random B of this size, and then solve with Gaussian elimination that we just had again.
Are you going to upload the file that you...
Yes, I will upload the file. That's not a problem. And this is how you time things. Okay? All right. This should be fun. All right. So, what we will see next time, one of these things, forward elimination and back substitution, takes longer time. And second thing, there's a lot of problems where if I solve, what changes my right-hand side is the change in the external condition, but the internally system, let's say that I have a system of pipes, okay? My coefficients in A don't change, it's B that changes. So we can actually cut things down by solving AX, when I'm solving AX is equal to B with multiple sides B, so I can do forward elimination only once. And then use and store the result, then I can just use to solve for different sides B. And that can cut some of this time. And that procedure is called so-called LU, left up triangular or lower triangular, upper triangular, LU decomposition of A. And that's our topic for the next time. But that's actually something that saves this time when solving this. But I'm going to let you feel that time first before we move on to LU decomposition. All right? And then LU decomposition is the last topic for our exam on November 20th. See you on Wednesday. You're welcome.